In this chapter, we will consider gas-vapor mixtures and air conditioning. At temperatures below the critical temperature, the gas phase of a substance is frequently referred to as a vapor. The term vapor implies a gaseous state that is close to the saturation region of the substance, raising the possibility of condensation during a process. In the previous chapter, we discussed mixtures of gases that are usually above their critical temperatures. Therefore, we were not concerned about any of the gases condensing during a process. Not having to deal with two phases greatly simplified the analysis. When we are dealing with a gas-vapor mixture, however, the vapor may condense out of the mixture during the process, forming a two-phase mixture. This may complicate the analysis considerably. Therefore, a gas-vapor mixture needs to be treated differently from an ordinary gas mixture. Several gas-vapor mixtures are encountered in engineering. In this chapter, we consider the air-water vapor mixture, which is the most commonly encountered gas-vapor mixture in practice. We also will discuss air conditioning, which is the primary application area of air-water vapor mixtures. And the objectives are to differentiate between dry air and atmospheric air, and we will define and calculate the specific and relative humidity of atmospheric air while calculating the dew point temperature of atmospheric air, and we will relate the adiabatic saturation temperature and wet bulb temperatures of atmospheric air. We will also use psychrometric charts as a tool to determine the properties of atmospheric air and apply the principles of conservation of mass and energy to various air conditioning processes. First, let's look at the difference between dry and atmospheric air. Air is a mixture of nitrogen, oxygen and small amounts of other gases. Air in the atmosphere normally contains some water vapor or moisture and is referred to as atmospheric air. By contrast, air that contains no water vapor is called as dry air. It is often convenient to treat air as a mixture of water vapor and dry air, since the composition of dry air remains relatively constant, but the amount of water vapor changes as a result of condensation and evaporation from water bodies and even the human body. Although the amount of water vapor in the air is small, it plays a major role in human comfort. Therefore, it is an important consideration in air conditioning applications. The temperature of air in air conditioning applications ranges from about -10 to about 50 degrees centigrade. In this range, dry air can be treated as an ideal gas with a constant Cp value of 1.005 kilojoules per kilogram degrees centigrade, as you can see here in figure 14.1. They are relatively constant even when the temperature is changing. Taking 0 degrees centigrade as the reference temperature, the enthalpy and enthalpy change of dry air can be determined from these two equations that you see over here, where the enthalpy of dry air, H dry air, is going to be equal to Cp times capital T, and the enthalpy change of dry air, which is delta H, is going to be equal to Cp capital delta T, where T is the temperature in degrees centigrade and delta T is the temperature difference. It would also be very convenient to treat the water vapor in the air as an ideal gas. So, you would probably be willing to sacrifice some accuracy for such a convenience. However, it turns out that we can have the convenience without much sacrifice. At 50 degrees centigrade, the saturation pressure of water is 12.3 kilopascals. At pressures below this value, water vapor can be treated as an ideal gas with negligible error, even when it is a saturated vapor. Therefore, water vapor in air behaves as if it existed alone and obeys the ideal gas equation of PV equals RT. Then, the atmospheric air can be treated as an ideal gas mixture whose pressure is the sum of the partial pressure of dry air P sub A and water vapor P sub V. That you can see in the equation here, which states that the pressure is going to be equal to the sum of the partial pressure of dry air and partial pressure of water vapor. Since water vapor is an ideal gas, the enthalpy of water vapor is a function of temperature only. That is, enthalpy H is going to be H of T. This can also be observed from the TS diagram of water given in figure 14.2, where the constant enthalpy lines coincide with constant temperature lines at temperatures below 50 degrees C. Therefore, the water vapor in air can be taken to be equal to the enthalpy of saturated vapor at the same temperature. The enthalpy of water vapor at 0 degrees C is 2500.9 kilojoules per kilogram. The average Cp value of water vapor in the temperature range of -10 to 50 degrees C can be taken to be 1.82 kilojoules per kilogram degree centigrade. Then the enthalpy of water vapor can be determined approximately from the equations given here. Now let's look at specific and relative humidity. The amount of water vapor in the air can be specified in various ways. Probably the most logical way is to specify directly the mass of water vapor present in a unit mass of dry air. This is called the absolute or specific humidity, also called as the humidity ratio, and this is denoted by the sign omega, where omega is going to be equal to m sub v divided by m sub a, where m sub v is the mass of water vapor and m sub a is going to be the mass of air. The specific humidity can also be expressed using the PVRT relations by omega is going to be equal to 0.622 P sub V divided by P sub A. In this case, P sub V is going to be the partial pressure of vapor and P sub A is going to be the partial pressure of air. This also can be further expressed by 0.622 PV divided by P minus PV, as you can see in this equation over here, where omega is given in kilograms of water vapor per kilogram of dry air. And in this equation, the capital P is going to be the total pressure. So let's consider 1 kilogram of dry air. By definition, dry air contains no water vapor, and thus its specific humidity is 0. Now let's add some water vapor to this dry air. The specific humidity will increase. As more vapor or moisture is added, the specific humidity will keep increasing until the air can hold no more moisture. At this point, the air is said to be saturated with moisture and is called saturated air. Any moisture introduced into saturated air will condense. The amount of water vapor in saturated air at a specified temperature and pressure can be determined from equation 14.8 that is given in the text by replacing P sub V with P sub G, the saturation pressure of water at that temperature. The amount of moisture in that air has a definite effect on how comfortable we feel in an environment. However, the comfort level depends more on the amount of moisture the air holds, which is m sub V, relative to the maximum amount of moisture the air can hold at the same temperature mg. The ratio of these two quantities is called as the relative humidity and is given by the symbol pi. And using PVRT relations, you can also find pi by using P sub V divided by P sub G, where P sub G is going to be the saturated pressure at that given temperature. Now with the information that you have gathered thus far, try to do this problem. There's an air mass which is at 25 degrees Celsius and 1 atm, and the total mass of air is given as 1 kilogram, and the mass of water vapor that this air mass can hold is given as 0.01 kilograms. And if the maximum amount of vapor that the air mass can hold is 0.02 kilograms, find the specific humidity omega and relative humidity pi. If you did the problem correctly, you should be able to get these answers. So combining equations that we developed earlier, you can get the new equations that you see on the top of the slide. The relative humidity ranges from 0 for dry air to 1 for saturated air. Note that the amount of moisture air can hold depends on its temperature. Therefore, the relative humidity of air changes with temperature even when its specific humidity remains constant. Atmospheric air is a mixture of dry air and water vapor, and thus the enthalpy of air is expressed in terms of the enthalpies of the dry air and the water vapor. In most practical applications, the amount of dry air in the air-water vapor mixture remains constant, but the amount of water vapor changes. Therefore, the enthalpy of atmospheric air is expressed per unit mass of dry air instead of per unit mass of air-water vapor mixture. The total enthalpy, which is an extensive property of atmospheric air, is the sum of the enthalpies of dry air and water vapor. And using some mathematical relations, you can come up with this important relationship where you can see the enthalpy, simple H, is going to be the enthalpy of air mass plus omega Hg. Also note that the ordinary temperature of atmospheric air is frequently referred to as the dry bulb temperature to differentiate it from other forms of temperatures that will be discussed later. Now let's look at what dew point is. The dew point temperature, or T sub dP, is defined as the temperature at which condensation begins when the air is cooled at constant pressure. In other words, T sub dP, or dew point temperature, is the saturation temperature of water corresponding to the vapor pressure, or T dew point is going to be equal to T saturated at P sub V. This is also illustrated in figure 14.8. As the air cools at constant pressure, the vapor pressure PV remains constant. Therefore, the vapor in the air, or state 1, undergoes a constant pressure cooling process until it strikes the saturated vapor line at state 2. The temperature at this point is T sub dP, or dew point temperature. And if the temperature drops any further, some vapor condenses out. And as a result, the amount of water vapor in the air decreases, which results in a decrease in V sub V. The air remains saturated during the condensation process and thus follows a path of 100% relative humidity, or the saturated vapor line. The ordinary temperature and the dew point temperature of saturated air are identical. You have probably noticed that when you buy a cold canned drink from a vending machine on a hot and humid day, dew forms on the can. The formation of dew on the can indicates that the temperature of the drink is below the dew point temperature of the surrounding air. The dew point temperature of a room can easily be determined by cooling some water in a metal cup, by adding small amounts of ice and stirring. The temperature of the outer surface of the cup when the dew starts to form on the surface is the dew point temperature of the air. Now let's look at adiabatic saturation and wet bulb temperatures. Relative humidity and specific humidity are frequently used in engineering and atmospheric sciences, and it is desirable to relate them to easily measurable quantities such as temperature and pressure. One way of determining the relative humidity is to determine the dew point temperature of air. Knowing the dew point temperature, we can determine the vapor pressure P sub V and thus the relative humidity. This approach is simple but not very practical. A way of determining the absolute or relative humidity is related to an adiabatic saturation process shown in the TS diagram in figure 14.11. The system consists of a long insulated channel that contains a pool of water, a steady stream of unsaturated air that has a specified humidity of omega 1, which is of course unknown, and a temperature of T1 is passed through this channel. As air flows over the water, some water evaporates and mixes with the airstream. The moisture content of air increases during this process and its temperature decreases. Since part of the latent heat of vaporization of water that evaporates comes from air, if the channel is long enough, the airstream exits as saturated air, where relative humidity is going to be equal to 100% at temperature T2. This temperature T2 is called as the adiabatic saturation temperature. Using the thermodynamic relations that is described in the slide, you can come up with the two important relations for finding omega 1 and omega 2 for states 1 and 2 respectively. And the specific humidity of air can be determined from these equations by measuring the pressure and temperature of air at the inlet and the exit of the adiabatic saturator. The adiabatic saturation process that was discussed earlier provides a mean of determining the absolute or relative humidity of air. But this process requires a long channel or a spray mechanism to achieve saturation conditions at the exhaust. A more practical approach is to use the thermometer, whose bulb is covered with a cotton wick saturated with water, and to blow air over the wick. This can be seen in figure 14.12. The temperature measured in this manner is called the wet bulb temperature, or T sub WB, and is commonly used in air conditioning applications. The basic principle involved is very similar to what we discussed in the adiabatic saturation process. When unsaturated air passes over the wet wick, some of the water in the wick evaporates, and as a result, the temperature of the water drops, creating a temperature difference, which basically is the driving force for heat transfer between the air and water. After a while, the heat loss from the water by evaporation equals the heat gain from air, and the water temperature basically stabilizes. The thermometer reading at this point is the wet bulb temperature. And note that for air-water vapor mixtures at atmospheric pressure, the wet bulb temperature, or TWB, is approximately equal to the adiabatic saturation temperature.